Thank you, Dr. Ani, for the introduction. And good morning, everyone. My name is Deepti, and today I'll be talking about optimizing wound healing protocols using the Einstein dosimetry for photobiomodulation therapy. Now, before we get into it, I wanted to talk about a very... Oh, sorry. Can you hear me now? Okay, sorry. Now, before we get into talk, I wanted to talk about a very particular scenario in today's sci-fi movies where, let's say, the protagonist is on the deathbed and suddenly the light shines through and the next moment he's up and ready to fight the demons. Now, my study is a little bit about that. Don't get me wrong, it's not about fighting anyone, but it's about trying to see, is that even possible? Can we heal a person so quick with the lasers? Well, we know that photobiomodulation is being used to treat oral mucositis with using a specific wavelength, usually 8-10 nanometer. Well, we question, can it be optimized and can it be increased by and can it be made better by using a different wavelength? So we hypothesize that optimizing the clinical photobiomodulation protocol will enhance epithelial cell migration in vitro, leading to accelerated wound closure, thus improving wound healing outcomes. We start a discussion by looking at Arndt-Schul's curve that tells us that the level of stimulus is not linear to the cell action potential. As you can see, there needs to be a certain amount of stimulus to have a maximum action potential. In this case, we need to be around a region C to D to have the best treatment, and it's working. Now, it's also important to ask the question, if the treatments are already working, why is there a need to even improve? Well, current PBM is a low-dose phenomena, and it's important to take into account the energy that is released by each photon, because that would make a huge difference in the calculations that we'll talk further. Secondly, each wavelength have different penetrations, therefore different photon energy, which is also important to take into consideration. Thirdly, it's very common these days to combine these different lasers to make the treatment more attractive for the patients. But it's also important to see the implications of that and how the treatment will come out by combining those different energies. So that's when the Einstein factor comes in. So we start the calculation by measuring the tissue surface irradiance, that is the power, total power that is going to the surface of your skin per centimeter square. We then multiply that by the amount of time the laser is being exposed or the skin is being treated, multiply that by the individual photon energy of the particular wavelength that you're using. For example, let's say we have a smaller wavelength, 400 nanometer, will have a higher energy. Multiplying this all together will give us a photofluency, which is the final energy that is going to that region. Now, to make it more easier to compare, we divide that by a factor of 4.5 because we are trying to standardize the treatment to the wavelength 8-10 nanometer. So when we talk about Einstein, we are referencing it to the 8-10 nanometer. Now, what we do is we take all the theory and put that into the lab through our research. So we work with human keratinocytes or Hackett cell line. We have a confluent monolayer in a 35 mm Petri dish, and we perform a scratch assay and further do laser treatments. The images are captured through T0 time 0 when the dishes are treated with the lasers to T12, and then we again analyze it through ImageJ. Here you can see the picture of a template that we use to measure our scratch. So here you can see is a place where you can fix the 35 mm Petri dishes. And because we have these 2 scratches in per dish, we get 8 different areas of interest for each particular dish that which we further analyze, and then the mean of that is taken into consideration to again compare across. So the study one is to answer our first questions. Is there a wavelength that is better? And can we optimize it? So we work with 6 different wavelengths. Again, a few wavelengths up before 8-10 nanometer and after 8-10 nanometer. And we have 2 different versions of each wavelength. First one would be normal treatment time. So each laser will be treated for 300 seconds. And the second plate will be for adjusted time, For example, because as I mentioned, 450 nanometer is a smaller wavelength with higher energy, therefore less treatment time. On the other hand, 1064 is a longer wavelength, lower energy, so higher treatment time. So to get into methods a little bit, we plate the cells in 35 mm Petri dishes with a very high confluency to again perform the scratch. We keep it overnight, and the next morning we do a procedural scratch with a consistent 220 microliter pipette. We again then treat with lasers, and then later we do the imaging. This is an example of the scratch assay, and as you can see, the cells are definitely moving in most of the plates, but there are two major plates which have important results. So here we can see there is a graph that tells us the difference between the starting area and the ending area. The more difference, the more area has been covered by that particular, in that particular plate. So here we can see we have two important results. Firstly, we have found a wavelength that is working better than 810 nanometer. So that's 560 and 450 nanometer. Secondly, our optimization has worked, where you can see the 560 nanometer normal version. The Einstein version is working better than the normal version in both 560 nanometer and 450 nanometer. Now the second study is to again validate the previous results and to investigate the PBM signaling pathway via loss of function and gain of function studies. So we try and block the ATP to see if there is any role of that ATP in the whole dynamics. Secondly, we compare between proliferation and migration. Because one might question, why are the cells closing? Is it proliferation or is it solely migration? Further, we also augment TGF-beta to see is TGF-beta even further important in the whole procedure. The methods are pretty much similar. The difference would be putting inhibitors before the procedural scratch and keeping the inhibitors in the media for 30 minutes. After the scratch, we again change media and then further do the laser treatments. This is the example of the scratch assay, and we can visually see that TGF-beta, the closure is much better than even 450E, which again will be shown in this slide. So here we can see the closure in TGF-beta is much better, which again validates the fact that TGF-beta is hence responsible. For the N-acetylcysteine, which blocks the proliferation pathway, does not have a lot of difference compared to 450 nanometer, which tells us that proliferation might not be the factor. But migration, and again ATP, does have a main role. Ongoing studies are to investigate the scratch assays conducted under different environment, hypoxic, diabetic, and infectious. As we all know, in these conditions, the wound healing is not as good as it is in the normal conditions, which is why we try to see how would the optimization work in these different conditions. That was my research so far. Thank you for listening, and I would like to thank my team, School of Dental Medicine, University of Buffalo, and ASLMS for giving me this platform. Thank you.